Well, friends, let us proceed further. In my previous lecture, there was some problem with the internet connectivity, so I could not conclude the Smith orthogonalization method. In fact, the result was given to you, and you see that we have obtained the eigenfunction psi k of the Hermitian operator, and now this eigenfunction psi k is orthogonal to your eigenfunction psi I. So in so the conclusion, we say that we have the set of eigenfunction psi I, psi j, and psi k, right? And these psi I, psi j, psi k are normalized eigenfunction. Psi I and psi j are not orthogonal to each other, but we have followed a procedure and formulated a eigenfunction psi k which is orthogonal to psi I for the case of two-fold degeneracy. You can also extend this method for three-fold degeneracy, and I think I gave you a problem in my previous class that you take three set of eigenfunction of an Hermitian operator, let us say operator A, and you take psi I, psi j, and psi k are the three eigenfunctions belong to the having same eigenvalue, say small a, and you, uh, I think, find out uh, another eigenfunction using the method of orthogonalizations and find out a set of orthogonal eigenfunctions for the degenerate eigenfunctions having threefold degeneracy. Well, friends, with this information, now we will proceed further, and today we will do some problems about the commutator and some basic commutation relation. So you see, I have this example which I would like to discuss in this. This is a simple example. These two relation which I wrote here is a very important relation and which we will frequently use in many numerical problems. You see, the first relation is that commutator of AB with the C, the product of operator AB, that is the commutator of AB with C is equal to operator A with a commutator B, C, plus you have a commutator of A, C, and he is operating on B. This is a very important basic commutation relation you have to remember. And there is another relation that if you have a commutator of A with the operator product BC, that is given by commutator of AB operating on C plus operator B operating on a commutator of A with C. You see, I have given a derivation. You can derive this. So look at this derivation of the first relation. You see that there the first relation is a commutator of operator AB with C, and we want to derive this. This is we want to do this. So I take the left hand side. Look at the left hand side. The left hand side is a commutator of AB with C. And you see the commutator of AB, there is a definition which we know that commutator of AB is of A operating on B minus B operating on A. So look at your left hand side, look at this. Of course, please concentrate here. The handwritings are very small. Please concentrate. This is the commutator of AB with C. So you have using this relation, AB is operating on C minus C is operating on AB. So this is your left hand side. Now you take the right hand side. So right hand side is A with a commutator BC with A commutator of AC with B. You look at this is the right hand side. Now I first solve this commutator of B with C. So I'm keeping A constant as a operator A, right? It is not disturbed, and you see that commutator of BC is B operating on C minus C operating on B. And now you have a plus sign, so you have a plus sign. You see the commutator of A and C, that is A is operating on C minus C is operating on A. This is a simple relation, commutator, and it is operating on B. And now let us open the bracket. So if you open the bracket, that is A operating on product BC minus A operating on CB, and then there is a plus sign AC operating on B minus CA operating on B. So you see these two operator product ACB with the minus sign, and this is operator product ACB are having equally the position, so they cancels each other. So you get ABC minus CAB, and this is your right hand side, and left hand side is also same, ABC minus CAB. So left hand side is equal to right hand side. So this equation is justified. Similarly, I'm giving you the homework that you please solve this using the same method. So I request you that these two basic computation relation you please remember, because we have to use many times. Now there is another rule which we want to understand, that if you have the operator position operator x, this is operator x which represent the dynamical variable position x, and this is px which is basically a momentum operator. This is basically a representing a dynamical variable momentum. This is the operator for dynamical. So for every dynamical variable we have an operators in quantum mechanics. So for position we have x, and for momentum we have a px. So we have a x and px. Px is in one dimension, so we can write minus I h cross d by dx, if you remember. So now what we want to prove that a commutator of x with px raised to n. Look at this, a commutator of x with px raised to n. This you want to prove that the commutator of x with px raised to n is always given by n times ih cross px raised to n minus 1. This we want to derive. So this law also you have to remember. Suppose n is equal to 2, so it's x px square. So the answer will be 2 times ih cross px raised to n minus 2 minus 1, that is px. Suppose it is x px n is equal to 3, then it is a commutator of x with px to the power of 3. So the answer will be 3 times ih cross px raised to 3 minus 1, that is 3 px square. So it will be 3 ih px square. Now let us derive this commutator relation. This is also a basic commutation relation. So I now you can see this relation. I'm taking the left hand side. So this is my left hand side, x px to the power of n, and I split px to the power of n is basically a product of px raised to n minus 1 into px. So this product will gives you px raised to n. So now I have this commutator which is similar. I consider x equal to a, px to the power of n minus 1 is operator b, and px is operator c. So this is basically a basic commutator relation of a with bc. So this one I can use this law, that this operator, this commutator is analogous to a basic commutator of A with BC. This you can see, where A is your X, right? Uh, Please remember, right? And then your B is basically Px raised to n minus 1, and C is Px. So you can use this relationship. So it is now, if you see, so it is a commutator of A and B. So commutator of A and B is commutator of A and B, that is a commutator of x px raised to n minus 1. So I write x px raised to n minus 1, right? Then the operator C is px, so I write down px here. Plus, so this is a plus sign. The operator B is px raised to n minus 1. So you see I write down px raised to n minus 1, and you have an operator AC, that is commutator of A and C. A is x and C is px, so I write down x px. I hope you understand this step very clearly. Now you see this commutator of x with px, they do not commute with each other, and which we have studied in my previous classes also, that x does not commute with px. So this commutator is always given by IH cross. So this is IH cross px raised to n minus 1, which I am writing here. So this is IH cross px raised to n minus 1. And this commutator I am keeping as it is x px raised to n minus 1 px. Okay. Now once again you see I am keeping this term as it is IH cross px raised to n minus 1. Okay, and now I split a px to the n minus 1 into the two part. So I'm keeping as x as it is, and this px raised to n minus 1 is nothing but a product of px raised to n minus 2 into px, because this product will give you px raised to n minus 1, and this commutator is operating on px, so this px is remaining as it is. So I'm keeping this px here. Now you can see the relation. So this is IH cross, so IH cross remaining, and then px raised to n minus 1, px raised to x minus 1, keeping as it is. Now again, this is a basic commutator which is similar to the commutator of ABC, right? Where A is x, right? B is px to the power of n minus 2, and C is px. So again you simplify this commutator with this basic law. So this you can see this I'm keeping IH cross px raised to n minus 1. Now this is basically a commutator of AB operating on C. So commutator of A with B. So you see commutator of A is x, B is px raised to n minus 2. So I'm keeping here. And you see you have to write down the operator C. Operator C is px. So I write px here, plus you have operator B. So operator B is px raised to n minus 2, the px raised to, and a commutator of A with C. Commutator of A with C, A is x and C is px. So I write x px and operating on px. Correct? So now let us once again simplify this term. So you can see this IH cross px raised to n minus as it is. These I'm keeping as it is x px raised to n minus 2. You see, and this px is multiplying with this px is giving you px square. Right? Why px square appears? Because this px and this px gives you px square. So this term you can write down, and now you see this is px raised to n minus 2, and multiply by with px gives you px raised to n minus 1, and this is again a commutator of x px which does not commute, and that gives you IH cross. So you have IH cross px raised to n minus 1, and again IH cross px raised to n minus 1. So that gives you 1 plus 1, 2. So that is 2 IH cross px raised to n minus 1. And again you have a commutator of x px raised to n minus 2 px square. Again we will commute this commutator, right? So you can see now this commutator can be, sorry, I'm sorry, let us once again come to that point. So now you see this commutator I want to commute, I mean I want to compute, I'm sorry, I want to compute. So this term 2IH cross px raised to n minus 1 I'm keeping as it is. And now again I split px raised to n minus 2 into two parts. So this is x as it is x. Then it is px raised to n minus 3 into px. This product gives you px raised to n minus 2 px square. Okay, fine. So now you can see, so that is why you can write down this 2IH cross px raised to n minus 1, the term remain as it is. And now again this is a commutator, basic commutator law. A you see operating on BC. So you can see this again, I use this law. You can now work out this law, and this is now very clear that I open this term. And once you open this term, you will see that the answer which comes out to be equal to 3 IH cross px raised to n minus 1. This is the term 3 IH cross px raised to n minus 1 plus a commutator of x px raised to n minus 3 px cube. So this way you can you can continue this. So you see, ultimately, you know, this you once you continue, then you will get the next term x to the power x px raised to n minus 4, and again you continue, it give to x px raised to n minus 5. So finally, when you go up to the nth time, you will have the expression, the answer, because this term will disappear, because you get px to the power of 0. And finally, if you continue this process up to nth time, you will have the answer n times IH cross px raised to n minus 1. I hope it is simple, one can calculate. I request you, after this class, you once again you do this calculation by yourself and verify this rule. Okay, and now today I have selected some problems, so let us go for another problem, which I would like to explain, that show that the commutator of you see, I have the nested commutator here. You have the inner commutator is commutator of x with h, and you have the commutator of x, then a commutator of xh, and that gives you the answer minus h cross square by m. This is we want to derive. Okay, this we want to derive. So look at that here. H is the Hermitian operator. Hermitian operator is p square by h. I'm sorry. Please excuse me. H is a Hamiltonian. Is an Hamiltonian operator. Please excuse me. So H is an Hamiltonian operator. So H is equal to p square by 2m, where p is momentum, and in 3 dimension we write px square plus py square plus pz square divided by 2m. Okay, and now our problem is we are talking about x. So we have this particular problem is given in one dimensional because we have a position operator x, right? That is given here, which is representing the dynamical variable position x. So here I can write in one dimension, so that is giving you the Hamiltonian of this is equal to px square by 2. So now, first to solve this problem, what I have taken, I consider you first take the inner commutator. You solve from innermost commutator to the outermost commutator when we do this computations. So I take the inner commutator. The inner commutator is a commutator of x with h. So I take x as it is, and h I is replaced by px square by 2m. So it is px square by 2m. Since 1 upon 2m is constant, I can take it outside from the commutator. So it is 1 upon 2m, you can take it outside, and it is basically a commutator of x px square. So again, you see, this is a commutator of 1 upon x px, I'm sorry, 1 upon 2m x px square. So I split px square into two parts, px into px. So again, this is a commutator of, you see, commutator of A, B, C, which I'm writing here. Commutator of A operating on operator product BC is a commutator of AB with C and with B, and you have a product of B with a commutator of A, C. So here, let us first calculate this inner commutator using that basic law of commutator. So this is 1 upon 2m and 1 upon 2m. Now this I'm using, this is basically a commutator of A with B. So commutator of A with B is xpx, so it is xpx. Then the operator C, so you operator C is px, so it's operator px, plus operator B is px, so px. And a commutator of AC, so commutator of AC is xpx, so it is xpx, right? Now you can see that commutator of x px is IH cross. So it is IH cross px, and again this is a commutator of IH cross. It is a number, so I can keep a px IH cross equal to IH cross px. So I can write IH cross px. So it is a 2 times IH cross px, right? And into 1 upon Tm, 2m. M is the mass of the particle. So IH cross upon m into px. This is the inner commutator. So you see that we have got the inner commutator. So now you look at, this is our problem. This is the basic commutator we want to compute. So we want to commute x. We want to compute a commutator of x with a commutator of xh. Now commutator of x with h is given by IH divided by m into px. So I am keeping this commutator. I am keeping the value of this commutator IH cross px by IH cross upon n is, this is a constant number, because mass of the particle is constant, h cross is a reduced Planck constant, I is imaginary number. So this you can take it outside. So IH cross by m is taken outside, and it is basically a commutator of x px, and commutator of x ps is IH cross. So IH cross by n into IH cross I square is -1. So it is minus h cross square by m. So that proves the problem which is given to you. Look at your problem here. See, this is what we want to prove, minus h cross square m, and that ultimately we have calculated minus h cross square by m. So this is ultimately giving you that how you can use a basic operator law. Right now, there is another interesting example which I would like to discuss. That you have one eigenfunction is given, psi of x is constant a, exponential of minus x square over a square, exponential of I p0. 0 is a subscript here, x h cross, and find you x. You have to find out what? Find a scalar product of x with pxi. There is a comma missing here. Please, there is a printing mistake. So here you put a comma, and you have to find out. Sorry. You have to find a product of x pxi. I'm sorry. Here you have to find out a product of x with pxi. So you have to find this. So this is not a scalar product. You have to find a product of x operating on pxi. So you see, I wrote here x pxi. You have to find out this product, operator product. Okay. So you have operator product x px operating on psi. So I'm keeping the value of x as it is. Now you have a px. Px is minus IH cross del by del x, one dimension. I'm keeping this. And psi, your eigenfunction, I'm keeping the eigenfunction a exponential of minus x square over a square, exponential of I p0x over h cross. So this I'm keeping. This you can, I think this you understand. So now you see x, so I'm keeping x, minus IH cross is a constant number, so I'm keeping minus IH cross. This constant a is a constant, so I'm taking outside, and I have this differential operator, right, that is operating on the operand exponential of minus x square over a square, exponential of IP0x over h. So this is the differentiation with respect to x, and these are the two exponential function, and both are function of x. So we can use the product law, right? So I will use the law of product for a differentiation. So here, before we proceed, you can see this constant I'm keeping as it is, x minus IH cross I'm keeping minus, and this constant a I'm keeping constant a. And now you see, first I'm keeping this exponential function constant. So I'm keeping exponential of minus x square over is constant, and I differentiate del by del x, del by del x of the another of exponential function, exponential of I p0x over h cross. And now what I will do, you see, I differentiate this. first exponential function. So I differentiate del by del x exponential of minus x square, and I'm keeping this constant. So this exponential function is remaining here. So now you can see, I'm sorry, there is a problem. Yes. So here you can look at this expression. This exponential factor remain as it is. Now this is a differentiation of this. So differentiation of this is, first of all, it will become the exponential of I0 x over h, and del by del x of IP0 x by h cross gives you IP0 over h cross. So this is known to you. Then similarly, this is the differentiation of exponentials. So first exponential function remain as it is, and you have a del by del x of minus x square over a square, and del by del x of minus x square over a is minus 2x over a square. So I'm keeping minus 2x over a square, and this factor remain as it, the exponential function remain as it is. Okay, so now you see this in both these, the term number 1 of the square bracket and term number 2 of the square bracket, the exponential term is common here. Here exponential of minus x square over a square, exponential of IP0 x square, here also exponential of minus x square over, and an exponential of IP. So you can take it outside. So I am taking this exponential term outside. So inside the bracket you have a IP0 over h cross, and there is also a factor minus 2x over a square. So I can write this factor here, right? Okay, and now you can see, uh, fine. Okay. Now you can see I multiply this minus IH cross with this square bracket term. So you can see this is your x. So I'm keeping x at this constant a, I'm keeping here. So x is kept here, the constant a is kept here, and I multiply minus IH cross with I. So h cross cancel, and this is I into I gives you I square is minus, and this minus minus gives you plus. So it becomes you P0. Now again you can see this is a minus sign here, and this is a minus sign gives you ultimately plus sign, and it is 2IH cross. So 2IH cross x remain as our a square. And this is your a I kept here. You see the a exponential of minus x square by a square exponential of IP0x. This is your eigenfunction itself. Look at your eigenfunction. This is your eigenfunction psi itself, a exponential of minus x square and exponential of this. So here you can write, you see, simply x, right? This is your x, and this is the square bracket term 2IH cross x over a square, and I write P0 here operating on psi, right? So you can see here, this is the way you can uh, calculate this. Now, similarly, I am giving you homework that you can find the product, operator product Px x psi. See, look at this. Here you have calculated x Px psi. Okay, x is operating on Px psi. And now I am saying that you calculate Px x psi, because x and Px does not commuting. So you have a Px x psi, and the answer you will get, this is I have calculated. The steps are not shown here, but if you calculate the product Px x operating on psi, operator product Px x operating on psi, you will get minus IH cross psi plus x, this square bracket term 2IH cross x over a square P0 operating on psi. This you will get. You please verify. This is your homework problem. You can do this these computations after this class is over. Please verify this answer. I have given the direct answer. The steps are not mentioned here. Now let us go to the next step, and today we will see some properties of Hermitian adjoint. I have already explained the property of Hermitian operator, and in fact Hermitian adjoint also I have discussed. but I think it is the right time to once again revise the meaning of Hermitian adjoint, because it will help us to solve many problems in quantum mechanics. You see, for any arbitrary wave function, if I have an arbitrary wave function psi 1 of x and psi 2 of x in one dimension, I can have any ordinary operator. It's not an Hermitian operator. So if you have an operator A, and if you take a scalar product of psi 1 with A psi 2, there is a scalar product of psi 1 with A psi 2. Look at this. And if A is not Hermitian, then it will be not equal to A psi 1 psi 2. If A would have been a Hermitian operator, then you will have a condition psi 1 with scalar product of psi 1 with A psi 2 will be always equal to the scalar product of A psi 1 with psi 2 that we have discussed. So if A is not Hermitian and ordinary operator, then you have a not equal to sign. But there is a possibility that you have another operator B such that the scalar product of psi 1 with B psi 2 instead of operator A, if you have an operator B, in that case you get the scalar product of A psi 1 with psi 2, right? So in that case, you see, when you are taking a scalar product with A psi 1 with A psi 2, and here you are getting a scalar product of psi 1 with B psi 2, you have some operator in possibility that it will be equal to the scalar product of A psi 1 with A psi 2. In that case, your B is considered as the Hermitian adjoint of operator A. It is known as Hermitian adjoint of A. So your operator B is known as Hermitian adjoint of A. And since there is a symbol, the Hermitian adjoint on operator, Hermitian adjoint of operator A is written as A dagger. You have A to the power, I mean, this is A raised to dagger. This is the dagger sign. So you write down A dagger. So A dagger represents, it is the Hermitian adjoint of the operator A. Please remember. So we can say that your B is a Hermitian adjoint of A. So when your B is a Hermitian adjoint of A, so Hermitian adjoint of A is known as A dagger. So B is equal to A dagger. So B operator B is the Hermitian adjoint of A. And when operator B is a Hermitian adjoint of A, this condition will satisfy. Okay, now our basic rule is that we want to derive some law for the Hermitian adjoint. Suppose A is Hermitian. Then suppose if suppose A is Hermitian, then I can write psi 1 A psi 2 is equal to A psi 1 psi 2. So you can see this condition, this equation psi 1 B psi 2 equal to A psi 1 psi 2. Now if A is Hermitian, then psi 1 A psi 2 equal to A psi 1 psi 2. So you see the left hand side of these two equations are same. So we can say that the operator B is nothing but operator A, right? In that case, if A is Hermitian. If A is Hermitian, then B is always equal to A. So if I write down A here, B is equal to A. So I can write down A dagger is always A. That means if A is a Hermitian operator, then Hermitian adjoint of the operator A is operator A itself. This is a very important law in quantum mechanics, that if A is a Hermitian operator, then the Hermitian adjoint of the operator A dagger, is always equal to the operator itself. That is, A dagger is equal to A. That means Hermitian operator is basically a self-adjoint. You see, Hermitian adjoint operator A, you know, that is equal to A here. So I wrote here that operator A, that is the Hermitian operator A, is a self-adjoint operator. Please remember, Hermitian operator A is always a self-adjoint operator. That means if you take the adjoint of A, adjoint of Hermitian operator, that is you take A dagger, so A dagger is always A, this condition. So please remember that the Hermitian operator is a self-adjoint operator. It's a self-adjoint. And that's why I can write down the condition for a self-adjoint operator, or the Hermitian adjoint of an operator. A dagger is a Hermitian adjoint of an operator A. So I can have this condition that psi1 is a wave function, and you are taking a scalar product of psi1 with A psi2 is always written as scalar product of A dagger psi1 with psi2, where A dagger is a Hermitian adjoint of A and A dagger is always A because A is a Hermitian. So this law is very important, and we want to use this law for several basic relation which we want to establish today for the Hermitian operator. Hermitian operator is a very important operator in quantum mechanics because you see generally all dynamical variables we are measuring, and these all dynamical variables when you measure their values are always real. So majority of the dynamical variables are basically associated with the Hermitian operators. So we will work for several numerical exercise to understand the properties of the Hermitian operator and the adjoint of the operator, right? So Hermitian adjoint of an operator, it's a name which we can say. So first of all, we want to derive the very important law, and I want to derive that, show that A dagger is equal to A. So these we want to derive. So if you want to derive this this important relationship, so I take two arbitrary wave functions psi1 of x and psi2 of x in one dimension. So I take this, and now what I do to derive this, I take the scalar product of psi1 with A psi2. Okay, now you know A is a Hermitian. If A is Hermitian, then it is a self-adjoint. So I can use this law psi1 A psi2 is equal to A dagger psi1 psi2. This is the law which we can use, right? So I can use this law A dagger psi1 psi2. So this you can write because A is the Hermitian operator, and Hermitian operator is a self-adjoint operator. And if it is self-adjoint operator, you can have a Hermitian adjoint. So I can write this Hermitian adjoint here. Now I'm taking the complex conjugate both the sides. I'm taking the complex conjugate both the sides. And so as you can see this psi1 A psi2 star, I'm taking the complex conjugate, and here also I'm taking a complex conjugate of A dagger psi1 with psi2. So look at this here. And now, if you see this complex conjugate, so this scalar product one can write down this equal to because this is the law. The scalar product of psi1 A psi2 with the complex conjugate is nothing but a scalar product of A psi2 psi1. That means if you have a scalar product of psi1 psi2, the scalar product of psi1 psi2 is always a scalar product of psi2 psi1 and whole raised to complex conjugate. So I write this A psi2 psi1. So this you see here I mentioned this, and similarly here also I just change the first parameter, first factor and second factor. The second factor becomes the first factor, and so you see this way, the second factor and the first factor become the second factor. So this you can write, right? I hope you understand this step. And now you see this is remaining same A psi 2 psi 1. And now you see this law. A dagger, A is Hermitian. If A is Hermitian, using this law, this psi 2 A dagger psi 1, right? Psi 1 A psi 2. So there you can see psi 1 A psi 2 is A dagger psi 1 psi 2. So I can use this law for the Hermitian operator, and so you can see A dagger psi 2, A dagger psi 1, because this A dagger, so this is A dagger, this is A, so this instead of A, you have a dagger here, right? So you put a dagger, so this is A dagger psi 2, A dagger psi 1, and now you can see this. So ultimately you can see A psi 2 psi 1 is equal to A dagger psi 2 with psi 1. So this ultimately you can write here that adjoint of you see this dagger, A dagger, you see, it gives you A. This is a simple relation, and which you have to remember in quantum mechanics, and I have to use these applications for various examples and some other concept which we would like to work out when we start for learning formulation of quantum mechanics and postulate of quantum mechanics. Now there is another law which one can prove, that if you have the addition of two operator A plus B, right, and if you take the adjoint of A plus B, right, adjoint of A plus B is adjoint of A plus adjoint of B. A dagger, that is you see Hermitian adjoint of operator A, B dagger, that is Hermitian adjoint of operator B. So you have the arbitrary wave function psi 1x and psi 2x, psi 1x and psi 2x. So now you can see here I am writing psi 1, right? Uh, and I am taking the scalar product of psi 1 with A plus B psi 2. Look at this, right? So this is psi 1, and I am taking the scalar product of psi 1 with A plus B psi 2. And using this law, because A is Hermitian, B is Hermitian, so A plus B is also Hermitian, which we have discussed. So we can write down A plus B dagger psi 1 psi 2. Please remember this, right? Now this scalar product of A plus B, which I have written here, you can split it into two parts. So this will be a scalar product of psi 1 with A psi 2, and a scalar product of psi 1 with B psi 2. It's very clear. One can write down this entire scalar product can be written as a scalar product of psi 1 with A psi 2 and a scalar product of psi 1 with B psi 2. And here you can see this term is remaining as it is, A plus B dagger psi 1 psi 2. Now you know again your A is Hermitian, so I can write down this psi 1 A psi 2 is A dagger psi 1 psi 2, and this also write down B dagger psi 1 psi 2, right? So I can write using the property of Hermitian, using this relation. This is the relation. Here also I can write down B dagger psi 1 psi 2, and this term as these are keeping as it is. So now I can combine these two terms, because this is A dagger psi 1 psi 2 plus B dagger psi 1 psi 2, right? So you can combine A plus B dagger, right, psi 1. This is A dagger operating on psi 1, this is B dagger operating on psi 1. So ultimately it is A dagger plus B dagger operating on psi 1 psi 2 is equal to A plus B, right? A plus B dagger operating on psi 1 and psi 2. And that's why you see now ultimately you get a derivation that A dagger B dagger equal to A plus B dagger. And now I have a final relationship which we will discuss. Look at this final relationship. Now I'm giving you the exercise. I have done these calculations, but you do this a problem for homework. You have a AB dagger, right? The product operator product AB dagger, and you have to prove is equal to B dagger A dagger. I have written these steps here, but I hope that this calculation you do by yourself, work out this problem and derive it that A B dagger equal to B dagger A dagger. Friends, I will stop here, and once again, next lecture we will take more problems related to the commutators, Hermitian operators, and then we will start to learn postulate of quantum mechanics. I'll stop here. Thank you very much.